we've taken a look at automatic differentiation, also known as Autodiff, and we focused on the reverse mode. In the reverse mode, remember, we have a forward pass and we have a reverse pass, and the kind of the key word or the phrase that you'll often hear for the reverse pass is called backpropagation, and I want you to be familiar with that because that's really what we mean by the reverse pass. And in this video, I just want to show you how this is actually applied to AI and machine learning, as far as not the let's build the context, but let's use the terminology that we would in neural networks. So when we looked at our example, we took a function and we decomposed it into simple arithmetic parts. And that's a great application of the chain rule, though oftentimes this is not what we're purely trying to do. What we're usually purely trying to do is apply at each, what we call neuron, some sort of function to the incoming data. And so we often start off with some sort of vector. Could also be a matrix, but maybe this vector contains information about an image. And that image, maybe the goal is you want to have an input of image data and an output telling you, yes, it appears that the image is that of a golden retriever, or no, it is not. So maybe the input is the image and the output is a yes or no as far as classification of the image. Regardless of the application, though, what we're aiming to do in our identification process is we are essentially going through the reverse mode, so forward pass and back propagation, many times until we've minimized a specific output called a loss function. And a loss function you could think about as an error. And we want to make that error as small as possible. And in doing so, when we then answer, yes, it is a golden retriever, no, it's not, we know that we're answering that based on minimizing the error in our projection. Now, are we going to make mistakes? Of course. But the aim of this process is to minimize that loss function. Now, each of these, what we'll refer to as neurons, okay, so this data is going to pass through. And I'm just looking at a very simple case of this. This is going to represent a single neuron, and the neuron kind of, you think about the brain, it's sort of a brain in and of itself. So it has this neuron, and at this stage, it is going to take the input x, and it's going to apply some matrix multiplication to it, a1 times the original x that went through, and it will add, and maybe we'll just refer to this as x0, because notice that it's always taking the, there should be a0, x0 plus b0. So that is going to produce a function at that stage. It's going to be called fi, and that's going to be the output of this. And that fi is going to produce the next value of what we'll call x. We'll just call this output x1. And that's going to produce another vector, which is then going to go into, say, another neuron. And there we're going to compute an f2. And this f2 will be some other matrix times x1 plus b1. So it's a linear matrix arithmetic here. And so this will kind of continue passing onwards until we get to the final neuron. And then from the final neuron, we'll just say that this is f sub n equals a sub n minus 1 x sub n minus 1. Notice that the current function is based on the incoming / previous values. And then we get an output that will represent the loss function. And when we compute the derivative of the loss function, we have all of these different parameters. And the parameters in this case, the quantities that we want to adjust are these matrices and these vectors. And so we're going to have this parameter space, which is sort of going to be a function of what we'll refer to as all of the A's all of the a's. So we'll just call this, what do we want to call it? I guess it's already a matrix, but it'll have a0 through an minus 1. And then it'll also have all of these vectors, b0 through bn minus 1. Now, as you can tell, this is actually a lot of inputs into that function. And so even though we're feeding it, you might think, well, isn't this the input? Well, it is, but as far as we can't control the data, what we're trying to control is how we manipulate the data. And so then as we start to compute each of these partial derivatives, notice we could potentially have a lot of them with respect to a lot of specific input parameters. And so based upon that, when we go through this reverse mode, right? So we do the forward pass, and then we do the back propagation, and we sort of continue in this cycle. Eventually, we'll minimize this, and this process we'll learn more about. It's called gradient descent. So in this case, these don't necessarily represent, they are kind of basic arithmetic functions. It's the same structure each and every time, but it's not like in our example where we said, every addition will represent one piece of the function, but notice that it does apply basic arithmetic operations each time. Now, the actual function that is being applied here, which we often write as a sigma of these quantities here, there are many structures of this function, but the common ones are what are called logistic sigmoid, or the hyperbolic tangent, or the ReLU, which stands for rectified linear unit. These are specific to that application. We won't go over them here, but we'll learn more about them later. And so it's just important that as you're working through this, you're making sense of each of these neurons, and as you work backwards, of course, there might be multiple inputs. You may have X, Y, and Z. That's just a simple case of 3 inputs. And the simplest case, right, is where these don't in any way feed into one another. Because if they do, then you have to account for the chain rule. If X feeds into this neuron as well, then you have to, when you're doing the back propagation and computing the partial derivative, you've got to take both paths that lead you back to X. So if you had something like this where, say, these 2 inputs went into here, and maybe X also went into an input by itself, and then maybe Z went, and then maybe, eventually they got combined. I'm going to make this real straightforward here. And let's say they all then got combined, and then we received our output, which maybe we call f of X, Y, Z. And as we backtrack, like I said, we have to think in terms of following each one of the paths when we backpropagate. And as we label each one of these, let's say here we call this A, B, and C, and then this over here maybe is D. Then we have to backtrack using backpropagation. Of course, over here we'll have df dd, df dd, and following the chain backwards, we'll have dd derivative with respect to A, and then the derivative of D with respect to B, and the derivative of D with respect to C. Notice that I'm not actually giving functions here. I'm not actually stating what they are, because we're not calculating anything here. We're just trying to show the logic of how each of these produces its own derivative. And then back here, this guy will be dA dx, and this little pass here will be dB dx, and this one here will be dB dy, and then this one here will be dc dz. So as the reason I want to provide some sort of formula for this is because, of course, it depends on how a specific input is feeding into, say, multiple neurons. But if we wanted to know df dx, we could certainly follow all the routes back that would take us to x. And that's the key when you're working through this, right? So there's going to be 2 routes. So I'm going to put a plus sign here. And then one of them is going to be following back this way. That will give us 1 route. So let's add those together. So the first derivative there as we pass through will be d. Oh, we forgot 1 here. This should be df Oh, we do have that, dd. I'm sorry, my handwriting's a little sloppy. This should be df dd right here. And so we have df dd. Now that's going to be 1, right? Because f and d are the same, and the reason we're labeling it d here is because this actually could go, produce one output and then also lead into another output somewhere else. So df dd will be 1, but maybe if we had another output, it would not, for that second function. And then as we backtrack, all we have to do is multiply the derivatives that we encounter on the way back to the start, and then dA dx. We could always check our work. We should always just make sure that our derivatives lead us with df dx, and notice that they do. And then the other route back, which I'll just do in a different color just to differentiate them, no pun intended, would be this way, and then back this way right here, and then back this way right here. So that'll be our second term. So it'll be df dd, but then following the purple route, we'll have dd db, and then finally we'll have db dx. And again, we should observe that those cancel and give us df dx. So that's kind of the best, I think, general way to visualize these, is when you lay it out and you follow all the paths backwards, that you could form these. Now, a computer can do this as well, but as far as the logic in so doing, it has to have some way of, in that reverse pass, keeping track of all the ways that one would get back to x or back to y. And we could again do a similar procedure for y. In this case, there would only be one term because it would be df dd, dd db, db dy. For df dz, we'd have df dd, and following back dd dc, and then dc dy.